Hello everyone, thank you for joining this webinar. Today I will be demonstrating new features for renewable interconnection studies in ETAP 24. Spotlight on compliance and power plant operations. My name is Mohammad Zadeh. I'm a Chief Product Officer at ETAP. In today's agenda, first we will have a quick introduction on renewable interconnection studies. Then we will look at customer challenges. After that, we will spend most of this webinar on demonstrations of new features of ETAP 24 for grid interconnection studies. Finally, I will summarize this webinar. As the global power sector rapidly transitions towards sustainable energy, the importance of grid interconnection studies becomes paramount. Grid interconnection requirements or codes are technical specifications which define the parameters that a facility connected to a public electric network must meet to ensure safe, secure, and optimal operations of the electric system. The facility can be a power generation plant, solar farm, wind farm, or any other grid-connected source. A typical grid interconnection standard or code addresses various aspects of power plant performance. A comprehensive study that covers various aspects of the power plant operation, such as normal operation, fault, dynamics, harmonic, and transient response is required to ensure that the interconnecting power plant complies with all required specifications. Here I have two examples of IEEE standards for grid interconnection requirements at transmission IEEE 2800 and distribution IEEE 1547. As you see, these standards have several pages, 178 and 136 pages respectively, asking for many requirements to be compliant. Standards and codes related to interconnections of renewable power plants and systems define many requirements, both at the points of interface and common coupling of individual inverter-based resources known as IBRs. These standards cover various performance requirements, including but not limited to voltage and frequency right-through, active power control, reactive power control, dynamic active power support under abnormal frequency conditions, dynamic voltage support under abnormal voltage conditions, power quality, negative sequence current injections, and system protection. Learning and manually checking the compliance for each requirements against these standards or codes require lots of skills and time, so it would be very costly. For instance, in the case of reactive power capability requirements, it is essential to run hundreds of load flow studies and compile the results considering many operating limits of assets within the power plant to determine overall power plant reactive power capability and grid code compliance. Further, manual grid code compliance study can be prone to human error and interpretations of the standard. ETAP combines extensive modeling capabilities with advanced solution algorithms, enabling you to undertake the wide range of studies required for grid connections and grid impact analysis of wind parks, PV generations, and other renewable energy power plants. Various study modules in ETAP enable conductions of all required interconnection studies, including but not limited to load flow, short circuit, protective device coordination, transient stability, unified dynamics and protection, harmonic analysis, as well as code simulations with electromagnetic transient programs. In addition, ETAP offers 3 dedicated modules for grid code analysis: grid code harmonics, grid code load flow, grid code transient stability. Also, we have smart inverter elements that handles all required smart inverter functionalities required in the different standards, especially IEEE 1547. Besides, ETAP offers Power Plant Controller with its digital twin in ETAP that makes it very reliable and easy for engineers to evaluate grid code dynamic performance using ETAP Power Plant Controller. You can check ETAP website to learn more and see our various solutions related to interconnections of renewable systems. In this webinar, we will focus on the ETAP 24 major enhancements for reactive power capability analysis. Now let's look at ETAP 24, and let's start by looking at rulebook. We go to References, Rulebook, and we open Capability and Control Rulebook. In the ETAP Capability and Control Rulebook, you can find many international Greek code rulebooks, and ETAP is continuously adding new rulebook to cover more regions. User can add their own rulebook as well. First, let's look at the British rulebook G99 2021. PQ profile, QV profile, PV profile, and pHz profile. This standard only has a capability curve for PQ and QV profile here, okay? In the case of the PQ profile, the rule defines the required reactive power capability at different active power values. And for QV profile, this rule defines required power factor capability at different voltage level. For instance, here we say that at 100% voltage, the power factor can be between 95% and minus 95%. So that's what basically it says at 100% voltage. Or in case of PQ capability, what we are saying here is that at 100% power, the megawatt absorption and generation should be between 33%. While at the zero power here, or 20% power, the minimum that the standard applies the requirement, the absorption should be around 12%, while the generation should be still around 33%. Such rule can be selected in the ETAP study case to check if the power plant complies against this Greek code. Now let's look at the equipment capability curve. So if you look at the list of the rulebooks here, you see there are two samples. Let's look at the typical 1630 kilowatt inverter. This rulebook allows users to enter the reactive capability curve in the form of the PQ, or P versus power factor, at different voltage levels. So there's one difference, major difference between the Greek code requirement versus the equipment. The equipment also that has dependency on the voltage. So in this case, as you see that the PQ capability is defined at different voltage levels. So basically we are saying that at 100% voltage, this inverter can provide 24% reactive power and can absorb 40% at the 100% voltage at different active power range. Or you can see capability at 85% voltage or 115% voltage. For each project, users should enter the equipment capability curve based on the data sheets or information they receive from their inverter vendor. For wind turbine generator, AC PV array, and inverter elements, user can select an equipment capability curve defined in the rulebook as megawatt limits. Now let's take a look at where we can do that in a PV array. So if I go to the PV subsystem here, look at the PV array, go to the inverter editor, and look at the capability curve. We can assign an equipment capability rule to this inverter. Means that this inverter is going to use this capability curve if in the generation page, the megawatt limit is selected as capability curves. Keep in mind that capability curve is only supported in unbalanced analysis. Now let's take a look at the wind turbine generation. In case of wind turbine generator, so in the rating page, if we select the megawatt limits as capability curves, then in the capability page, you can assign the rulebook to define the equipment capability curve. Power priority, including active and reactive power priority, can be also selected by users. Both rulebook selection and power priority can be set globally in the study case if it makes sense to save time and avoid their assignments one at a time. Typical renewable power plants include many inverter-based resources, the step-up transformer, collector cables, the plant transformer, and possibly additional reactive power sources such as capacitor banks or STATCOMs. Furthermore, users must define the planned point of measurements where the grid code requirements are applied. So in this case, this is our point of measurement. ETAP 24 offers a new user interface that significantly simplifies renewable interconnection studies. And that interface is Power Plant Editor. So if I go to the renewables or if I go to the project ribbon, you're going to have access to Power Plant Editor. Now, with the magic of the Power Plant Editor, user can select the plant energy resources. As you see here that by default right now for this plant, I have all my PV arrays, STATCOMs, and wind turbine generators. If user has a large project with many power plants, user can add more plants. User can use the zone, area, and region to be able to find or assign the energy resources of the plant to the defined power plant. Also, the rated power can be manually set or can be automatically calculated by the power plant editor. Also, the point of measurements can be defined by a meter at the point of interconnections and be assigned to the defined power plant. In ETAP 24, all grid code and renewable related modules are grouped under the Renewable Study Group in the new ribbon bar user interface to provide easy access for users that perform grid interconnection studies. For reactive power capability analysis, user must select the load flow grid code mode. Prior to ETAP 24, the grid code analyzer controller was used to perform reactive power capability analysis. In ETAP 24, the grid code analyzer controller is replaced with the study case options that significantly simplify and accelerate the study setup and multiple type of scenario generations. First, in the info page, you select simulation as grid code. And then in the grid code page of the study case, user can select a grid code capability rule with which compliance is required. User can select the power plant they want to study from the power plants defined in the power plant editor. The reactive power capability curve can be globally assigned to the inverter-based resources of the selected power plants or the entire system. Power dispatch priority, active or reactive priorities can be globally assigned to the selected power plant, inverter-based resources, or the entire network. PQ and VQ sweep active power and voltage ranges and resolution can be adjusted by the user. The capability sweeping algorithm has been enhanced in ETAP 24 to consider possible operating and design violations. Additionally, user can choose to avoid or ignore any critical or marginal alerts such as overload or overvoltage or undervoltage as defined in the alert page of the study case. Most default values for sweepings are good for typical studies. And with a few adjusted settings, users are ready to perform the grid interconnection studies. Now let's run a grid code load flow for this plan while both STATCOMs are disconnected. ETAP will run many load flows, sweeping active power, reactive power, and voltage, as well as calculating P and Q at the power plant point of measurement. Once analysis is completed, ETAP will generate a comprehensive Excel report. The Excel report contains project information, specific study case settings for grid code load flow analysis, device capability rules used by power plant IBRs, detailed informations of all device capability rules used in the analysis, detailed information of all the applied Greek codes PQ and VQ or V power factor capability rule, and then PQ sweep tables and charts for the detailed voltage set point. So in this case, we have it for 95, 100, 105 PQ curves, and then V power factor for 15% as well as 100% power. User can easily determine compliance with the selected Greek code capability requirement. As you can see here, the Greek code is not compliant, as the Greek code required capability curve, which is the red one in this case, fails to fall within the power plant capability curve, which is the pink one. In other words, the plant is less reactive power capable than it's supposed to. The same with the PQ curves. The plant Greek code requirement, which is the red one, does not fall within the pink curve, which is the plant capability curve. So in this case, the plant is less reactive power capable than it's supposed to. Now let's go and add the StatCom to the system. So we go to the capability StatCom and we run the case where the StatComs are now connected to the system. For this case that we added a StatCom, now let's look at the charts that we have. As the Greek code capability report indicates, the Greek code capability requirements are now met. If you see here, for voltage 95%, the Greek code requirements falls within the plant capability. If you look at the 100% voltage, we have the same case. The Greek code is met. If we look at 105%, we see the Greek code is met. We look at the 15% power and look at the voltage versus power factor. As you see that, again, the Greek code is met. The Greek code requirement curve falls within the plant capability curve. The same thing is for the 100%. So this report can be an easy evidence for the clients to show that the plant with this size of the StatCom, in this case is 28 megawatt, results in meeting the Greek code requirements. This study, in fact, not only checks compliance against the Greek code, but also it is an essential tool to size reactive power resources in the power plant, such as capacitor banks or StatComs, to meet the Greek code reactive power capability requirements. In ETAP 24, the report manager supports Greek code capability analysis. This means that users can generate Excel report without the need to rerun the analysis. This is a great advantage, as users can use Scenario Wizard as a placeholder to maintain study information without needing to separately relate the output database file name to the Excel report file name. For instance, if you would like to regenerate the report for the case that a StatCom was not in the system, we can simply load the corresponding scenario. Let's go here to capability new StatCom, capability new StatCom and load. So we can just load that, go to the report manager, go to the results, Greek code capability, and generate the Excel report. If we want to look at the case with the StatCom, we can simply go to the scenario, load the scenario, press OK, go to the report manager results, Greek code capability, and generate the Excel report without the need to running the report. And basically we have the report as expected. Besides significant enhancements in the user interface of the Greek code load flow in ETAP 24, the sweeping algorithm has been altered to avoid operating constraint defined in the alert page of the study case, such as equipment overload or overvoltage and undervoltage condition. With this new algorithm, users can compute the capability curve at the power plant point of measurement without violating any alerts. Let's look at the same example, assuming that alerts are not considered. So here I have this study case that we are avoiding any alerts and constraints, and I have created another study case that we are not avoiding any alerts. This means that we let the alerts to happen, but they're not gonna limit the capability curve during the analysis. I have run both study cases before, so I'm gonna first plot the capability curve where we added the statcom, but in this case, the alerts are avoided. And let's go through each page. Here you see that in the tables that we have, there is no marginal alerts at V equals 95%, but there's one critical alert as you see for case 18. So what does that mean? If you look at the case 18 in the first column, you see here is that case 18 refers to minus 56 megawatt Q and 76 megawatt generations. Basically, it's somewhere around here, okay? So as it says that at this point, the three-winding transformer at the point of interconnection issues an overload alert saying that the reactive power imported, because of the high reactive power import to the plant, we're gonna have an overload condition. There's one small alert here at 100%, and there is no alerts at 105. If I go to the V and power factor curve, you see that there's no alert at 15%, but there are several alerts at 100%. So let's go and plot the chart here. So this is the chart that we have for the plant V power factor capability curve. Now, if I go to ETAP and go and look at the same study case, this time the difference is that we are not considering the alerts in the capability curve. So what we are going to do, let's go and create the Excel report for this capability curve through the report manager. And let's go to the last page here as well for the comparison. So in the last page, if I go to the last page here, we can now compare. Here is the capability curve without avoiding any alerts. This is the one while we are not avoiding any alerts. And it is very clear the capability curve or the plant is actually more capable while violating the alerts. But if we say that no, violating alerts is not accepted, then the capability curve would be smaller. As you see, the capability curves are calculated in the tabular format for all possible cases. You have cases excluding all the alerts, excluding all critical alerts, and including all alerts. So ETAP generates all the data for all possible alert considerations, but only plots the one that is selected in the study case. This helps users determine which assets or part of the system play a role in limiting the capability curve, while only the selected violation options selected by the user appear in the Excel charts. If a renewable power plant has an energy storage, the active and reactive power dispatch of the energy storage typically depends on the application. Sometimes we don't want the energy storage to be used as the main reactive power resource because we want it to use it for certain auxiliary services or maybe do renewable smoothing. So ETAP grid core load flow analysis by default does not sweep the energy storage active and reactive power. If user wants to do that, user can go and check storage dispatch in the study case. So what will ETAP do? ETAP is gonna command the energy storage with the same proportion as other devices. So if you're commanding, let's say PV arrays to generate 10% active power and 10% reactive power, we're gonna command the battery to discharge 10% and generate 10% reactive power. Again, in this case, energy storage, we never command to absorb active power, but we command generations and absorptions of the reactive power along and in proportions to other devices in the plant. Now, if user wants to say, no, I do not want the energy storage to be used in that form, user has to manually set energy storage generations or absorptions, whatever, active and reactive power manually in the system. But this option allows to have some control, whether we consider energy storage in a power sweep or not. As mentioned throughout this webinar, ETAP 24 grid code load flow offers significant enhancement to speed up study setup and enable users to generate reactive power capability in a matter of few clicks. Another new feature towards this goal is the automatic voltage range selections for PQ and VQ sweep. If the grid code has a voltage reactive power requirement, which would be QV profile page, if the grid code has this page, the rulebook has defined the curve here, the minimum and maximum voltage here, the minimum and maximum voltage in this case is going to be 95 for the minimum and 105 for the maximum, can be used automatically as a voltage range within the PQ and VQ sweep. So in the PQ and VQ sweep, if you do not know what's the range and you want to use whatever is in the grid code, by just this selection is going to use it from the grid code. Again, this minimizes the amount of user settings that wants to be adjusted and making it more intuitive and much easier for user to utilize this tool to do grid code analysis. Now with that, let's summarize this webinar. The manual analysis of grid interconnection studies can be time consuming and very complex. For a simple reactive power capability compliance, many scenarios needs to be generated. The results of all these scenarios need to be compiled to determine PQ and VQ curves at the point of measurements of the power plant. ETAP offers a dedicated module that automatically sweeps active power, reactive power, and voltage as per the grid interconnection requirements that is stored in ETAP rulebook to generate a comprehensive capability report that can be directly submitted to the system operator. In the ETAP capability and control rulebook, you can find many international grid code rulebooks, and ETAP is continuously adding new rulebooks to cover more regions. This saves lots of time for the users to fully comprehend the standard or grid code and manually check the compliance against them. Users can also add their own rulebook. ETAP grid code load flow analysis can record and avoid operating constraints through alert settings to ensure that required reactive capability can be achieved without imposing any overload or over and under voltage conditions. ETAP grid code load flow is one of the many modules and solutions that ETAP offers for grid code studies. You can explore our website to find other ETAP products such as grid code transit stability, grid code harmonics, and power plant controller. Thank you for paying attention to this webinar.